Today we're going to talk about electric potential, right? So the first thing, I will give a definition to electric potential, and then I will explain its physical meaning in details. Then we are going to derive the electric potential due to a point charge, a discrete single charge, right? And then we can use that result to expand, and we can have the information for whatever distribution of charge you have. You can have multiple discrete charges, or you can really have continuous charge distributions. Then I will talk about the strategies in finding electric field intensity, the general rule, and then we can talk about more details about electric dipole, right? So, the definition of electric potential actually starts from one of the null identities we covered for vector analysis. If you still remember, well, examination is coming in 1 week, so this is a good chance for you to review the covered topics. So if you have a scalar function, you perform its gradient, and then you perform the curl. By definition, it will become zero. We talked about this physical insights. If you perform a gradient to a scalar function, it will be normal everywhere, right? So if you have the vector is normal everywhere, you perform its closed loop integration, curl, you don't have any net circulation. So the definition of electric potential is really closely linked to this null identity and the second postulate we made for electric field intensity. We assumed E fields are conserved fields. If you have a conserved field, its curl must be zero, right? So if you compare this, the second postulate, to the null identity, curl of a conserved vector field must be zero. And null identity tells you curl of a vector is equal to zero. If the curl of that given vector is equal to zero, that vector can be represented by the gradient of a scalar function, right? So we compare these two directly. Now we can say E, our E field, which is a vector, because its curl is equal to zero, we can write E in some form as the gradient of a new scalar field. So our E field can be defined as the gradient of a scalar field. And that scalar field is called the electric potential, right? So basically these two are closely related. A conserved vector field can be written as the gradient of a scalar field. They are both functions of position, right? But one thing you note, one thing very special is I have added a negative sign to it. So actually, the E field intensity as a function of space is the negative of the gradient of the electric potential, also a function of space. So think about it. Why am I adding that negative sign? What's the importance of the negative sign? so let's come to the blackboard. Assume I have two planar charge distributions. We already went over planar charge distribution. You know how to calculate the resulting E field intensity. So in this case, I have one planar charge with positive charges. The second one is having negative charges. All right? Due to a planar charge distribution, we have constant E field intensity. So I can quickly draw the field lines for you, right? The electric field lines starts from a positive charge and ends on the negative charge. So in this case, all I have to do is draw the electric field lines. So these are my E field lines. Okay? You start from the positive charge and ends up on the negative charges. The next thing I want to know is, well, somehow the electric potential is a scalar function. It's not really having direction. But after you perform the gradient of it, then you have a vector. So vector comes with amplitude and direction. So fictitiously, if I can draw some lines, right? So these lines are somehow perpendicular to my electric field lines. So I can somehow say, oh, I have potential A and potential B, right? So on this yellow line, on this point, this point, this point, they should have the same potential. And on this point, this point, this point, as long as they are on the same line, they have the same potential B. Right? So now is a decisive point. If you were to compare the potential between A and B, which one is having higher potential? Think about it. Electric charges with positive sign usually are taken as the ones having higher potential. This is like the mountain, and this is like the valley, right? The height of the mountain are usually taller than the valley. So it's our custom to define the positive charges are having higher potential, right? So in another way, you can understand it as the field lines start from the location with higher electric potential and ends up at the locations with lower electric potential. Okay? So this point is having a higher potential as compared to this point. The next question is, so that we know V is increasing as you walk from the negative charge towards the positive charge, right? As you can see, the direction of increasing V is anti-parallel or reversed direction as compared to the E field lines. So what about gradient of V? Gradient of V comes with an amplitude and a direction. Now refresh your memory. As we covered about gradient, by definition, gradient points in the direction where you have the maximum increment of that scalar function. So when you have gradient of V, it also points to the left. Right? This is the direction where you have the increasing electric potential from the negative charge towards the positive charge. So your E field is from the left-hand side to the right-hand side, from the positive charge to the negative charge, but gradient of V is in the reverse direction. It points from the negative charge to the positive charge. This is the direction where you have increasing electric potential. Okay? It's in the reversed direction where the E field is pointing to. So this is why we have to include the negative sign. Alright? So this is just a mathematical definition, but the mathematical definition with or without the negative sign, it can all hold. But to make it physical meaningful, to our understanding, positive charges are having higher potential as compared to the negative charges. So we need to add this negative sign to take into consideration that del grade V is pointing in the reverse direction as compared to the E field lines. Alright? Again, the physical meaning. So you have a lot of electric field lines. So the physical meaning of electric potential is, well, if you have a charged particle sitting somewhere in space, you have electric field intensity distribution, and you move the charged particle along certain path, you need to contribute work to it, right? So suppose in this case, we have a charge, particle, and if we take that charge and we start from location B and we move it to point A, how much work do we need to put in so that this charge can be successfully moved from position B to position A? That amount of work divided by its charge is your electric potential. Alright? So the amount of work done in moving a charge from one location to the other divided by its charge, by definition, is your electric potential. Right? Again, E equals negative grad V also tells you if you have a charged particle, if it moves along the electric field line, you lose electric potential. Right? So if you have a charged particle sitting somewhere here where you have the higher potential, it moves in the direction of your electric field line, right? Along it, you lose potential. So in this case, you don't have to devote work. You actually gain some energy, right? You don't have to give the energy into the particle. That particle loses potential, so somehow you gain energy. So this is again the same thing, but viewed from a different perspectives. Right? Okay. So this is in the differential form. So if you know electric potential as a function of space, you can perform the gradient and remember to take the negative sign when you arrive at the E field intensity as a function of space. In the integration form, if you already know the E field intensity profile and you want to know how much energy difference or potential difference you're having when you move the particle from point 1 to point 2, you perform the line integration and you take the negative sign. That's your potential difference. This is your work, right? This is your work. And work divided by that charge gives you the potential difference. Okay? So, are we clear from the audience? Are there questions from the audience? Right? So basically I spent a lot of time telling you why the negative sign is necessary. Okay? Because due to the fact gradient of V is pointing in the direction where you have positive changes in that scalar function. But the E field is pointing in the direction where you have negative changes. So they are reversed. Okay, so you have to take account of that negative sign. Right? So let's take a look at the problem. We have a single charge. Right? Single charge with amount of Q. We already know the E field intensity distribution for a single charge. That's from Coulomb's law. Right? Q divided by 4 pi epsilon 0 r squared. R means the distance from my observation point to the charge. If we want to find the potential of a single charge, remember, the previous equation tells us the absolute value of the electric potential is really arbitrary. Okay? What we care about is the potential difference between the 2 points. So whether this is 5 volts or this is 10 volts, it doesn't matter. All we care about is their difference. So for a single charge, we can define a reference potential. And usually we want to have the reference being set at infinity. Meaning we're very, very far away from that point charge. And that's where we define the potential to be 0. Okay? For r equals infinity, we define its potential as 0. So as we move from a very far position and we walk towards the charge, we have, well, if it's positive charge, we're increasing our electric potential. So we can use our known fact. For a point charge, you have gradient, E field line distributions. We can just insert that into the equation and we perform the line integration, right? So in this case, a point charge resembles its fields, resembles its sphere. So we are using spherical coordinate. In spherical coordinate, as we change its radius, its dl, differential length, is simply r unit vector times dr, right? So this differential length making a dot product with an E field that is also pointing in the R direction, you can perform its direct integration. So basically, for a point charge, it sets up a scalar electric potential as a function of distance as its charge divided by 4 pi epsilon 0 r. So it's inversely proportional to r only, as compared to E fields. It's inversely proportional to the r squared, but E fields are also vector. Potentials are only scalar. Right? So this is coming from direct integration to our basic knowledge, our understanding, to Coulomb's law.